Thank you. The first thing to do is to compliment Markus. As he said, well, it was a kind of postdoc at least, but we met Markus when he wrote his book, very nice book, and it's a fantastic book, pedagogical view. I enjoyed a lot, and in fact, I was a member also of the bank, the jury for his Abilitour, and it was kind of a trap for me because as I was a member of the jury, I had to ask questions in German. And at that time, I was more or less okay in German, but now not anymore. I forgot completely. It's a pity. I don't speak anymore German. Maybe if I come back there 2 or 3 weeks, it will be okay. But and also, Markus came in Lumini, and we had a very nice. He came with Stephanie, and the baby were. Yeah. And so it was a very nice time in Marseille Lumini. It's a nice place. If some people of you know, there is a center the same than in Oberhof in Germany, the CIRM in Marseille Lumini, the Center for International Meetings. And before that, I was director of this center, so it was a very nice period for me. Okay, so I will explain the title later on. I would like to start. I can say some words about Marie-Hélène Schwartz. I was a student of Marie-Hélène Schwartz in my 3rd year university. And at that time, it was for students in Marie-Hélène Schwartz, it was quite difficult because she was a high-speed brain. And she was always having some ideas going after ideas. And so she was starting sentences and then another idea. So she was not finishing the sentence and starting a new sentence and so on and so on. And so sometimes it was for the student very difficult to follow Marie-Hélène Schwartz. And fortunately, at that time, the university student, it was in 1965, and university syndicates, they were doing copies of, they were asking to the professor to give the course before, and they were giving some kind of preprint, if you wish, of the courses, so it was possible with a friend of mine. We were before the courses. We were looking at the course and preparing questions for Marie-Hélène, and so it was very interesting at that time. And then I've continued to work with her after that for PhD. In France, it was called Doctor de Troisième Cycle. So for the PhD at that time, I made a PhD with Marie-Hélène Schwartz, and I wanted to make what was called the Thèse de Doctorat d'État, which is equivalent of Abilitour in Germany, habilitation, I think. And Marie-Hélène Schwartz told me that no, she was not. She did not feel that she was good for that, and so in fact it was a chance for me because she sent me to Henri Cartan, and I made habilitation with Henri Cartan. That was a fantastic period. And okay, so that's to introduce Marie-Hélène Schwartz, and she's a wife of Laurent Schwartz. Maybe you know Laurent Schwartz, but Marie-Hélène is. I will show you what she did in mathematics. She did very interesting things, and I will start in an elementary way. I don't hesitate to ask questions. If you have a question, you ask a question. If I can answer, I answer. If I cannot, I will say. But don't hesitate if you have any question to ask any question, okay? Even if you feel elementary question, no problem, no problem. There is no elementary question. And okay, so that's to start. Okay, so in fact, maybe another thing in introduction before what she did. So it is a theorem, Poincaré-Hopf Theorem for singular varieties, which is at that time even Poincaré thought that it was not possible to do that. And Poincaré had a counterexample that I will give you. And so during a long time, people was thinking that it is impossible to have a Poincaré-Hopf theorem for singular varieties. Maybe I remember to you Poincaré-Hopf theorem. So Poincaré. So that period is a period with many events in France. It is around 85 to 90. And so it starts with the funeral of Victor Hugo. So it's a period to give you some repair, I will say. And also at that time you have the first metro in Paris. And also you have Eiffel, which appear in my title. He was constructing his tower, that you know, Eiffel Tower. And Eiffel, he wrote on the tower the name of 72 scientists, French scientists, all men on the tower. It's engraved. You can see, even from the bottom, you can see at the first floor the name of 72 scientists, French scientists, all men. So recently, it's only from 1 year and a half, the feminist movement in France, they said, oh, hey, what is that? And so all movements like women in mathematics, women in physics, in chemistry, and so on, they met together and they made a program to have the name of 72 French scientists, all women, engraved on the Eiffel Tower. And this is successful. And the list of 72, 72 women, French scientist women, famous, all of them. And the list is already made. And among them, there are 11 mathematicians. 11 women mathematicians. And Marie-Hélène Schwartz is one of these 11. So the name of Marie-Hélène Schwartz will be engraved on the Eiffel Tower. That will be beginning of next year. It took a little time because we had a local election in France, and so it depends of the people in Paris to vote the budget, the money for that. So, but it will be next year, and we will be this event, which will be, of course, a very big event. And for me, it's fantastic that Marie-Hélène Schwartz has been chosen among these 11 mathematicians to be on the Eiffel Tower. Okay, but I come back to Poincaré because, as I said, I will speak of Poincaré-Hopf Theorem. In fact, Poincaré shows that if you take the Euler characteristic, Euler-Poincaré characteristic, on that point also I have, sorry if I give too much history, you interrupt me if you think that it's too much, not enough mathematics. But 10 years ago, Italian woman in mathematics, how do you love it?
Yeah.
Oh, okay. Yeah. So Claudia Labo. She's a student in history, not in mathematics, in history, but she was looking at papers of a monk, Italian monk, Francesco Maurolico. And she has seen that this guy, on 26 December 1977, if I don't mistake. Sorry, I wrote in the French way to write dates. Okay, so it was Christmas, and this guy, Francesco, this monk, was writing everything he was doing every day, writing the day and every day. On that day, he looked at the planar representation of the plateau polyhedra. The five. So you know that. In fact, you know that plateau polyhedra are not at all from Plato. Plato wrote this in his written things, but Plato says explicitly that the three first are from Pythagoras. The tetrahedra, the cube, hexahedra, and octahedra are from Pythagoras. And the two other, icosahedra and dodecahedra, are from a guy named Theaetetus. And this is Plato. Plato wrote this. And we say Plato because Plato wrote, but in fact, polyhedra from Plato are not from Plato. And we will see that Euler, Poincaré, in fact, this guy, he looked at the planar representation of the five Plato polyhedra, and he wrote that if you take the number of some of vertices plus the number of faces, that is the number of edges plus 2 for the five Plato polyhedra. So the first guy to write this formula was 200 years before Euler, and he wrote for the Plato polyhedra. But it's interesting to see that in fact this should be the Maurolico formula, and in fact you know that also Descartes is also in the. But I will speak during 3 hours of history. So okay, so. But it's good to know that the Euler-Poincaré characteristic, Euler did for dimension 2, and for surfaces, and Poincaré generalized for higher dimension. And the formula is that the Euler characteristic of M smooth manifold compact. And this is equal to the sum of indices of a vector field V and AI as isolated one. Singularities of V. Maybe I will recall this point a little later. But this is a Poincaré-Hopf formula. So Poincaré for dimension 2, and Hopf for higher dimensional. It's interesting that Hopf gave this formula for higher dimensional manifold, smooth varieties, but and he had a student, Stiefel, and Stiefel, and Hopf gave to Stiefel the question of generalizing this when you have not a vector field, but when you have a field of sometimes a field of frames. Okay, so yes, Hopf asked to his student Stiefel to see what can we say if instead of a vector field, you look at the frame of the airframe of vector VR, which is VR, such that the vector fields are linearly independent. And in that case, singularities are points where these vectors are not linearly independent. And this, so I will not speak too much on the characteristic classes in the real case, but so this is in the real case, M on M manifold that you can assume in some space higher dimension Rn, okay? And Stiefel made it, and in the same, more or less at the same time, Whitney made it. Whitney was in the States, and Whitney is famous also for this. So he made the same thing, generalizing the Euler-Poincaré formula for frames. And so these are the Stiefel-Whitney classes. I will not speak too much about them, but just to give you in history. And the common point Whitney with Boulder is that Whitney was climbing, and even there is in the mountains in I don't remember where exactly, but it's not so far from Boston. You have mountains with a ridge, which is a Whitney Ridge, because he was the first to climb this with another guy, but Whitney was so this is you know that in Boulder you have a lot of mountains you can climb, so a common point with Boulder. Okay, so these are Stiefel-Whitney, to give a little story, and but I will look at here, and as I said, this formula is not true in general if you have a singular variety. And the Poincaré was the first to give a counterexample, and this counterexample is picture that I like a lot, you know, the Pichet torus. The Pichet torus is a good example where this formula is not true. Why? Well, first of all, you can, of course, you know very well the vector field on the torus, tangent to the parallel. Okay, and you know very well that there is no singularity for this vector field, and also the Euler-Poincaré characteristic of the torus is 0, which is well the sum of indices because there is no singularity at all. Okay, so in fact, what did Poincaré is look at? Okay, so take this vector field now on the Pichet torus. Of course, your vector will have to vanish when approaching this point, which will be the singular point, say A, and then growing on this side. The problem is to define what is the index of the vector field in that point, because you know very well how to define the index of a vector field when you have a smooth manifold. Why? Because if you have a vector field V with a singular point, say A, so index V, A is a singular V. So, isolated. I don't know if I did here. Isolated, yes, I wrote. So isolated singular point of V. What does it mean? It means that if you have this point A, there is at least a neighborhood, there is a ball. Oh my God, when I was young, I was able to circle very well. No, it's more difficult. So you know very well that there is a neighborhood, as it is isolated singular point. There is a neighborhood of A. So we are here in some air dimension n, okay? So here, of course, is a blackboard, I have dimension 2. So you have a neighborhood, a ball, such that inside the ball, A is only one singular point of your vector field V. What does it mean? It means that on the sphere, which is here, your vector field is not zero. The vector field is not zero. So you can define what is called the Gauss map, as it is a Gauss. There's a lot of German people in that story. So you have the Gauss map. The Gauss map is, you take, in fact, you take the same picture that I will make here, but in fact, you have to do the same place. And like here, you have the point A, and for each point x, here, you have V of x, and you take a vector, which is W of x, which is of length 1, and which is parallel. Okay, so if I have x1 here, so W x1, and then I have this point, for example, x2, and I have here V W of x2. Let's say, what does it mean? It means same one. Okay, the picture is here. Okay, but I did on the right in order to not to confuse things. So you'll see very well that if you look at, you start from x1 and you make a cube like this. So here you will see that the point y1, y2 here, the point y will describe a circle of radius 1, okay, and it will describe a number of tours, positive, negative, and this number of tours is the index. So you can define the index because you are here in a manifold. So you have a neighborhood which is a ball, and the boundary is a sphere, and then you have, if you want to say in a better way, because the number of two, of course, in dimension 2 you see very well, but in there I know. So you have here the sphere which is n minus 1, here also. So you have a map which is this Gauss map from Sn minus 1 in Sn minus 1, and you take the homology of this map. You know very well that homology of the sphere, in dimension of the sphere, this is Z. So you have a map, gamma star, you will say, from Z to Z, and this is multiplication by an index, by a number, by an integer, positive or negative. Okay? So this is the index. The index is exactly the index appearing in this map here. But this is possible, as I said, because you are in the manifold. So you have a ball, you have a sphere. Here, that point, not at all. You are not in this situation.
What is the Euler characteristic of the hinge torus? Is that 1 or 0?
That is a good question. That is an excellent question. And like this, okay? You identify this with this with this, this with this. So you obtain sausage. Okay? This identification. And then you identify this point with this point. And this gives you the picture torus. So now you compute the number of edges, the number of vertices, the number of faces. And if I don't mistake, and if you don't mistake, you find that the number of vertices plus minus the number, so number of vertices minus the number of edge plus the number of faces, taking care of identification, of course. Okay, you have not to count twice what you identify. Okay, and this is, if you do not mistake, you find one. Okay, I let you make the computation exercise. Okay, so the Euler characteristic of this I will call TP or picture is +1. So what is the index of this singular point? I cannot use this method because it's singular. So I have the neighborhood of this point is not at all ball. Neighborhood of this point in the picture torus is a double cone. And so you cannot define an index. The only way, and this is what will appear later on in the Marie-Hélène Schwartz work, the only way to define an index here is in the ambient space. In the ambient space here, you can, on the torus itself, you can extend your vector field. You can extend it in the ambient space on inside this ball. Okay, so you extend on the sphere, you extend your vector field going through the sphere, through the ball, going like that. Okay, all parallel like that, just like that. Okay, so and in that case, you see very well that the index is 0 because you have all points are all W are all equal, so you don't move at all. The index is 0. Okay, and it corresponds well with two restrictions. In fact, when you look at this formula, the definition of the index, you see very well that A is a singular point, but the only one singular point. So, but it can be anything inside for the vector field. What you look at is not what happens inside. When you look at this Gauss map, you look at only what the behavior of your vector field on the boundary on the sphere. You don't take care of what happens. It can be anything. It can turn. The only thing is that A is a unique singular point. Here it's the same. What is important is what is on the sphere, on this sphere. Here. What is inside? No, it does not, no important at all. So, and this field is here. New vector field is entering and going like that. Okay?
So is that, so are you embedding the pinch torus, so in R3, and that's a two sphere around it?
Yeah. Huh? So I have looked at the two sphere in R3, in NE3. Okay? And so the vector field is entering like this. So the index is 0. And so we have seen that the characteristic is 0 and the index. And from elementary school, we know that 0 is not 1. Okay, so this is a counterexample. This was the first example that Marie-Hélène Schwartz was considering. And she said, what can we do? with that. What can we do? We said, okay, for this vector field, the result is not true. But can we find vector field such that the result is true? Okay. Euler characteristic we cannot change is 1. So is it possible to find a vector field for the picture torus such that the index in R3, because you cannot compute the index on the picture torus, as I said, because the intersection is not a sphere. You can compute only in the ambient space. So can we find a vector field such that the index should be 1? And that is exactly the first example of the discovery of Marie-Hélène Schwartz, which is the radial vector field and radial extension that we will see. Okay, so what she does is the following. Take again your picture torus and take again the ball. And I want to find a vector field such that the index is 1. That you know very well. Vector field such that the index is 1 is a vector field. You don't care what happens inside, as you have seen. Okay, one way on the sphere, because we just compute only in the ambient space, only on the sphere. On your vector field, you know very well. The vector field is radial, going outwards the sphere. What you have to take care is your vector field should be tangent to the picture torus at this point of intersection of the sphere with the picture torus. Your vector field should be tangent to the picture torus. And this circle here, and also this circle here. Okay. So now I have a point A, which is isolated singular point of my vector field, and the index is 1. But if I extend the vector field, what will happen? Maybe I will have another singular point. And in that case, it does not work. But in fact, Marie-Hélène Schwartz said, okay, no problem. And she extends this vector field in such a way that if you take the successive meridian, here the vector field is make an angle of 90 degrees with the meridian, it is orthogonal to the meridian, and then you will have a slope, you make a slope, the angle will be slower, okay, a few, and then more and more, when you take the vector like this, till on the opposite meridian, opposite to the singular point, it will be tangent to the meridian. Okay, you see very well how your vector field is going, from this circle to this circle. And also, of course, you make this parallel symmetric on the other side, so that you have a vector field which is well defined on the rest of the picture torus and without any other singular point. So you win. Yeah.
Can you explain again why I have index 1?
Here?
Yeah.
Because if you look at if you take this, if you take the Gauss map, you will have you will describe the sphere only once.
Oh,
The sphere.
it's
In fact, when you have a sphere, if you take a sphere of any dimension, okay, and you take this vector field going outwards, always index 1, any dimension. Take care that if you take the vector field going inwards, it will be +1 if k is even, And so +1 and -1 if k is oh, thank you. My God, even English is going. I did not say at the beginning of my lecture, but I am sorry that I don't speak English. I speak Franglish. You know very well my you see very well my accent, so I am sorry for that. Okay, so if V goes outwards, it's always +1, and if V is going inwards, +1 or -1, depending on the parity of the sphere, the motion of the sphere. Okay. So now, if we have this vector field, it's okay. You have a vector field which is radial. And this is the first example of the long story of a radial on the radial extension of Marie-Hélène Schwartz. This is the first example. So now, even for the picture torus, it's okay. Okay, if you take a radial vector field, radial from the isolated singular point. So now, if you have a singular manifold in general, you have no. If you have a singular variety, in general, you have no isolated singular point in your singular variety, but you have what Markus knows very well, stratifications. Okay, so if I take now singular variety, you have a stratification. What does it mean? It means that if you have, for example, you have this singular variety, you can stratify this. So you take the singular part here, the singular part is the cross. All other points are regular. They have a neighborhood which is disk without any problem. But if you take a point on this cross, you see very well that a neighborhood will be something like that, okay, which is absolutely not a disk. Okay, so you have inside the singular part. Okay, again, this is a singular variety because if you take any point here, of course, you have an interval that it's okay, a neighborhood which is a ball of dimension 1. Okay, but if you take that point here, the neighborhood is not at all an interval, it's a cross. So that point is a singular point. So you take the point itself, which is a singular point. So each time I take the singular part of the previous, and then I have the empty set. Okay, the stratification is given by filtration, a filtration of the space. This is an example of possible stratification, but of course you have many possible in general stratification. And I don't remember if I have 3 or 4 hours to speak. Because, my God, wow, it's awful.
The next talk is at 9 in the morning tomorrow morning. So.
No problem. No.
So
when you want,
yes, what is exactly the claim there? Because I can probably cook up other vector fields which give me other indices.
Yeah. So you have to show that if it is every vector field which is radial in a sense And the sense is that if you have isolated singular point, it's going outwards the ball in the ambient space, Okay, so this is the first definition of radial for dimension 0. Now, if you have isolated singular point,
this condition is only at the singular point.
yeah. The rest is okay. The rest the rest it should be tangent. And here you see that here you have what are the stratifications? The stratification are so here I have dimension 2. Inside I have dimension 1. Inside I have dimension 0. And I have 27. Okay. And the strata are the difference between both. So here, for example, in this picture, the first stratum is composed of these sheets, which are two-dimensional, and the cross is not at all element of the strata of dimension 2. So you have 8 strata of dimension 2 in that picture. Here you have the strata of dimension 1 will be the difference between x1 and x0. That means you have 4 strata of dimension 1. Okay, the strata are the difference between the two elements of the filtration. Okay, that's clear. And the strata are smooth, regular. So inside the strata, you can look at if you have a point in the stratum, you can take a disk and you have the boundary of the disk is a sphere. It's okay. So if your vector field has a singularity in the strata of dimension 2, is okay. You can compute without any problem the index. But if the singularity is here on the stratum of dimension 1, what can you do? You will tell me, okay, if my vector field is tangent to the stratum of dimension 1, then I can take a small neighborhood. Now it will be an interval, a sphere of dimension 1, okay? It will be a disk of dimension 1, sorry, and the boundary is a sphere of dimension 0, which are 2 points. Okay, so if I have a singularity here, I can compute also the index along the stratum. And in that point, we know already that it will be +1 because it's radial in the ambient. But you see very well that you have, for example, here, if I have a vector field, I have 2 possible computation of indices. If I have a singular point on this dimension 1 stratum, I can compute the index taking care of this segment, which is a pole of dimension 1, okay? And I can compute the index along the stratum of dimension 1. And I can also compute the index of this singular point in the R3 with a ball, the full ball of dimension 3. So I have 2 ways to compute the index if my vector field is tangent to the stratum. I can compute along the stratum of dimension 1, that will give me an index, and I can compute in the ambient space. And a priori, there is no reason for the 2 indices to be the same. Look at, I can give you an example. I can make a simple picture. If I have a dimension 1, I can take the vector field. Whoop. With a singular point A, the vector field like this. So in the index, it's +1. It's radial along the stratum of dimension 1. It is going outwards here, so it is +1 index. But you can extend this vector field in that way, or you can extend your vector field also in that way. And now, if you look at the vector field along in the ambient space, the index is 0. So the index is not the same along the stratum and in the ambient space. And Marie-Hélène Schwartz says that's not good. And she gave a counterexample. Well, I have no time to give a counterexample, but she gave a nice counterexample where the sum of indices is not good. It does not give Euler Poincaré characteristic because she says this vector field is not radial. It's radial along the stratum of dimension 1, but it's not. And she said, I need a vector field radial in all strata, not only in the stratum of dimension 1, but also in the ambient space. And how to do this? That is a discovery of Marie-Hélène Schwartz radial vector fields. She wrote a full book to explain radial vector field. Of course, knowing how she was thinking, but I will explain to you why there are some difficulties, okay? But what she did is the following. She said, okay, I will make some pictures in order to you to understand. If I have a stratum of dimension 1, S alpha, here, and suppose that you have a stratum of dimension 2 going here, so that S beta will be the strata of dimension 2. But it can be something like that, the same than the picture I gave. Okay, so you have S alpha here, and S beta at dimension 2, okay? But I will give the picture on the blackboard only, but you have to think of this picture at the same time. So she said, okay, I take a stratification, and a stratification satisfying. I have not the time to explain this, but where is Whitney? Disappeared. Here. So Whitney gave, for stratification, Whitney conditions. He said, the strata, they have to connect with some condition. They cannot go in any case, anyway. You have to impose some conditions. And if you look at the book of Markus, you will have the Whitney condition very well explained. I will give a little for you to understand because it's very important here. And the first condition is the following, and I will make another picture here. Here. If you have a stratum of dimension 1, S alpha, and this picture I will take two stratum S beta. So S alpha is in closure of S beta. Okay? And Whitney says, if I have a sequence of points xn in S beta, S beta 1, S beta 2, what is beta? Sequence of points going to a point y in S alpha. S alpha is in the closure, so you can research sequence of points. And Whitney says that if you have limit of xn for n goes to infinity, I don't write each time. S beta is smooth. S beta is a smooth in dimension 2. So for each point, you have the tangent space to S beta at that point xn, which is a two-dimensional plane. Okay? And Whitney says that if the limit of the tangent plane exist. It's not always the case. So, of course, you have the limit. You have the limit of planes like that. You have to think you are in a Grassmannian of two planes in R3, for example, for my picture, okay? And the limit is made in a suitable Grassmannian. So if this limit exists, you will have here the limit of equal T. This limit exists, then T contains the tangent plane to S alpha at y, at the point y, which is that, because S alpha is Prima Sonora. So this thing here is a line which is tangent to S alpha at the point y. And Whitney says, I want having this condition for each pair of strata such that S alpha is in the closure of S beta. Whitney shows that for all analytic complex, you wrote also for real, but an analytic complex, we will use much more in complex. Marie-Hélène Schwartz to use much more for. But for Poincaré-Hopf, it's in real. And Whitney shows that you can always stratify singular analytic space having this condition. Not only this condition, but another. This is Whitney condition A. But why is it interesting this? Because if you have a vector field along S alpha with a singular point in A, you are in an ambient space which is an Rn big one. You have a metric, you have anything necessary. So you can speak of parallel at each point X in S beta. You can take here, you have a tubular neighborhood, so you can project X will be in the point Y here, exactly like this. Okay, so 0 point X close to Y. And this vector V of Y, you can take the parallel, the value at X, which is the parallel vector of V of Y. You take the parallel. And with this condition says that so V of Y is here, and the parallel here is not necessarily in the tangent space, but the angle is small, because the limit of these guys contains the small tangent to the small strata. So the parallel makes a small angle here. The parallel W of X make a small angle with a tangent space at X to the stratum S beta. So you can project, because it's not, the projection is not zero. And Marie-Hélène Schwartz says, okay, I take the parallel in a small neighborhood of S alpha. I take all parallel. So you have something like that. Of course, it's zero. You have a disk of zero. Okay, so you take the parallel. Okay, and the parallel, that means the strictly parallel, and you project on the tangent to the big stratum at the point. You can do that, and it's not zero because of the condition A. And the condition B, I will not give you like the same way Whitney is giving the condition B, but the condition B, we say that if you take in your ambient Rn, you have your stratum S alpha, and you take the gradient of the distance at each point in Rn, the gradient of the distance to S alpha. The gradient to the distance of S alpha is a vector field, which is zero along S alpha, which is growing when you go far from S alpha, growing with the distance. So this gradient is something that I can represent like this. Here is 0, but it's small here, but it's growing as far as you go long distance from S alpha. So you have such a vector field, which is 0 here, and growing like that. I think you understand very well what she will say. She will say, I will call radial extension of my vector field, which is along S alpha. I will call radial extension the sum of the parallel and the transversal. So we have a vector field, which is like that. Here it's the original one. Here it is the transversal one. And I think it's not difficult to convince you that the index to vector field B at the point A along S alpha is the same, and the index of this sum that I will call V theta, which is a parallel plus the transversal. V theta, that A, in this case, ambient, the index is the same. You have the same index along the stratum and in the ambient space. And this is the main condition of Marie-Hélène Schwartz radial extension. And this is to imagine that you have to do that. It's fantastic idea. Fantastic idea. So you have a vector field for index will be the same. So now I can give the Poincaré-Hopf Theorem for singular varieties. I have to say that she wrote this in a note au compte rendu de l'Académie of Science in Paris. Note au compte rendu, I think you know the note. Rendu à l'Académie of Science Paris. 22 March 1965. I know very well the date because it's my 20th birthday. This date. So it's a coincidence, very nice coincidence. So she wrote this, and also the Chern classes. I will not have time to speak of Chern classes, but Poincaré-Hopf Theorem, I continue. In fact, yes, I have to say that I can give personal that during a long time I did not take care of my age. I was not taking care at all. In fact, I am something that you can be only 3 times in your life in n or n plus 1. So you can be only three times in your life in this age. And I have the 3rd one. So, so I didn't care my age. Continuing doing mathematics and so on, it was fantastic for me. And one day was something terrible for me. Absolutely terrible. That I realized, for me, you have a Poincaré-Hopf theorem is far away, is long, earlier characteristic is far, and you have new things like Roger theory and so on. So old things, new things. And for me, Chern classes were old, very old. Chern classes something very old. And I realized that I was older than Chern classes. That was terrible for me. So Chern classes were in 1946, and I was 1945. So And that when I realized, yes, that Jean Cassis, that I was older than Jean Cassis, it was, and then I realized my age. So I give you Poincaré-Hopf Theorem. So I will take an example. One. Like this, yeah. A very simple example. I have this singular point, and I have this one-dimensional strata, and I have two-dimensional strata. Okay? For this point, you know very well already. You have to take a ball. So we are in an R3 here. You take a ball, and you take a vector field, which is tangent to the strata, but going outwards the ball. The same here. So it's clear that if you take x0, is it still here, x0? Yes. X0 are points. So it's clear that Euler characteristic of x0 is the sum of indices. Because all indices are plus 1, and the Euler characteristic is the number of points. So it's clear. For x0, you have, well, Euler Poincaré-Hopf Theorem, which is true. For x0. For x1, what you do? For x1, this vector field here is tangent to the strata. So it is tangent to this one-dimensional stratum. And you can extend it. You forget completely the rest. You have a curve and a vector field entering in the curve, so you can extend along the curve. This is Poincaré. It's not mysterious at all. You extend your vector field, and of course you will have some singular points when you will extend your vector field. The vector field tangent to the stratum with some isolated points. Okay? AI. The same for all one-dimensional stratum. I don't picture for four. Okay? So you extend. And then you perform this radial extension of Marie-Hélène Schwartz, parallel plus transverse. And this you do in a neighborhood, in a tube, around your one-dimensional stratum. Exactly like this. And so for each this AI, which are points on this stratum of dimension 1, the index of your vector field along the stratum of dimension 1 is the same than the index in the tube. And you know, I forgot to tell, Poincaré-Hopf this boundary. You know very well that you have manifold with boundary. If your vector field is going outwards along the boundary, you know that you have the same. Some of indices. But if your vector field is going inside, this formula is not anymore true. You have to add Euler characteristic of the boundary. This is Poincaré-Hopf with boundary. I forgot to say at the beginning. Poincaré-Hopf with boundary says that. And you have exactly here what happens for x1. For x1, which are one-dimensional stratum, Euler characteristic of this will be the sum of indexes at this point, plus Euler characteristic of the boundary. But Euler characteristic of the boundary is this, that we know already. So Euler characteristic of x1 is, well, the sum of this point, indices at this point, computed either on the stratum or in the ambient, you don't care, plus this. So it is exactly the sum of all singular points of indices of all singular points which are in x1, either inside or at the boundary. Okay? And then, so you have also here a tube around this one. And you see very well a very nice property of your radial extension of Marie-Hélène Schwartz is that always the vector field is entering in the following stratum. Here it was entering in the stratum of dimension 1, and your vector field, you see very well that it will be going outwards of the boundary. The vector field is going outwards of the boundary. And this gives you exactly the fact that for this stratum here, S beta, Euler characteristic of the closure of X beta will be the sum of all singular points that you will have when you will expand inside the two-dimensional, plus Euler characteristic of the boundary, but this is X1. So Euler characteristic of X2 will be exactly the sum of all indices of all singular points inside X2 or on the boundary. So you recover completely Poincaré-Hopf Theorem for singular varieties. And that's very nice theorem of Marie-Hélène Schwartz. There are some difficulties. She wrote a book. And the difficulty is just to say, just one difficulty. One difficulty here is clear that you see very well that you have a vector field going from this and a vector field going from this. So here you have a competition between the two extensions. So she did with. And also the other difficulty is that, okay, so there are other difficulties. So she passes all these difficulties in a very nice way, but very complicated. And in fact, in a very recent, not recent, it's 2 years ago, with Thuy Nguyen, which is professor in Brazil, and Tadeusz Mossowski. Tadeusz Mossowski is a creator of Lipschitz stratifications. And we have shown that if you don't take Whitney, sorry, but if you take Lipschitz stratification, the difficulties encountered by Marie-Hélène Schwartz not vanish completely, but you can pass in a much more easiest way. This is for Poincaré-Hopf. For chunk classes, you take frames in the complex situation, and then you have to work. Okay, thank you.
It was super clear. Thank you. Very clear talk.
And so I am, no, on the contrary, I'm very happy. I thought that some people going in a chair like that, you will sleep during my lecture, but not at all. So I am very happy.
Actually, I have a very quick question because we have physicists and chemists here. So did Marie-Hélène Schwartz, did she look into possible applications in the sciences?
Yes, not directly, no, not directly. But I know that the Poincaré-Hopf theorem is used in a lot of sciences. If you